Alright, this is the Tutor Wizard. What we're going to do is we're going to find the Laplace transform of a piecewise defined function. I'm going to break it into 3 clever steps for us so that we can get a handle on what's going on. Step 1 is if you've taken a regular calculus class or you're an engineer and you've seen Math 100 and you've done a bunch of calculus and they give you piecewise functions, this is the lazy way actually of describing this piecewise function. We're going to use step functions and write them as linear combinations of these functions multiplied by step functions in a clever way. What they say originally is if you have an f of t who is defined as f1 of t, f2 of t, fk of t, then they have this horrible indices in the book, and then they have to say there had to be a bunch of switches. So this will be between t1 is less than or equal to t is less than or equal to t2, and then this will be t2 is less than or equal to, usually like this, and then t, and then strictly less than t3, and then this will have to be tk is less than or equal to t is strictly less, or actually in the last one it's you're larger than the tk greater than t is larger than or equal to tk, blah 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 blah. What are they saying here? Basically in ours all I'm going to match is we have f1 of t is equal to e to the t and f2 of t is equal to 1. We have 2 of these switch functions, and then we're switching at the time t equals 2 is where we're going to switch. What I want to do with that scenario is then once they have that, they're going to say we're going to write this as linear combinations of unit step functions. From this thing, they say we can write f like this. F of t can be written as f1 of t plus f2 of t minus f1 of t times the unit step function. I'll draw him in a second for ut1 of t, the time 1 where we switched. I get to erase the general f plus plus fk of t minus fk minus 1 of t in the last term times the unit step function of the last tk of t. That's how they're going to write that. What the heck does that mean? And there's no, so we're going to do it with just 2 switches, or with just 2 functions and 1 switch, and see what the heck they're doing, and then we'll figure out why they were actually doing that scenario. Why do I want it like this, or what is going on here actually? Let's re-describe this hot mess with just these 2 guys, and then we can get an actual handle. I really like this. This is really clever. Heaviside is the first person doing this, I believe. And what we're going to do is we get to turn, these are going to use turn functions on and off. They're like switches, light switches. And so what we want is in the first scenario, when we're in the first time, I erased it now, but when we're in the first time interval, we want this function to be on and the rest of these to be zeros. And then after we go into the second interval, I want this function to stop being f, and I want this one to start being f. So then I want this one to go away, and I want this one to turn on. Let's describe this scenario with these guys, and then you can see how they turn on and off in the 2 different intervals. For our function, f of t is equal to the first function, e to the t, plus, I didn't write down what the step function is, so I'll do that in a second, plus the second function minus the first function, 1 minus e to the t, times u2 of t. I don't like this notation. I don't know why they don't just write it like this, so I'm running the show. I've got the microphone. T minus 2. The shift, unit step function shift. What that is, what they're saying is u of t is the unit step function. He's on or off. He's 0 for t less than or equal to, for 0 up to some t naught. And then he's a 1 if t is larger than or equal to, actually, in this case, in the original one, he's 0 for t less than 0, and he's on for t larger than or equal to 0. That's the original one. The t naught is what I was just about to do. So then what is the shift guy? U of t minus 2 is just a shift. How would that be if we're using standard transformations, everyone? That would be a shift to the right 2 units. So all we're doing is taking that unit step function, which was 0, and then on, actually there's the open one, that's u of t, the unit step function, is off or on. Now what we're doing when we shift it by that guy, that's going to shift that function to the right 2 units. So all we're doing here is, if I want u of t minus 2. That is going to be 0 if t is less than 2, and 1 now if t is larger than or equal to 0, 2. And all that did was take us to the value 2, and then our function, our step function is 0 there, and then it turns on right at 2. And what do we multiply that by? The difference of the first two functions, because now watch what happens. It will turn these functions on and off. To see that before we go to the next step, so step 1 is this. Step 1 is write f as a linear combination of your piecewise functions multiplied by step functions. Once I do that, let's see what, before we move to the step 2 and apply the Laplace transform to this and use the linearity. It's Laplace transform is a linear transformation on these guys. Before I do that, what is this process doing? Can you see as the student why the hell we've made this move? If you can't see why we've made the move, you don't want to practice getting good at doing the move even. Why we've done this cleverly is it's going to say in this interval you're just e to the t. And then when we move out of this interval into this interval, it will become just this function 1. Let's look at that. When t is between 0 and less than 2, this says we're going to get f of t is equal to e to the t plus 1 minus e to the t times u of t minus 2, but we just looked at that. If you are less than 2, u of t minus 2 is 0. So that is just e of t, the first function. And so what that's saying is in this interval, that function will be off. So it killed this term, and in this interval, it's saying you are just e to the t. Then if I move into t larger than or equal to 2, what that says is f of t is equal to e to the t plus 1 minus e to the t times, now what is u? U is now 1. That's an open circle. So this is times 1. And cleverly, that's why we did it. It cancels those guys, and f of t is the second function. These step functions are turning the functions on and off. There's some kind of innuendo there, but let's just leave it like that. Step 1, write your function as a linear combination of the functions times unit step functions. Step 2, use the linearity, or the fact that the Laplace transform is a linear transformation, so that means it spits out scalars and it splits sums. Now I don't know how to apply the Laplace transform to that. Actually, those are the wrong brackets. Too technical. I really like Laplace transforms. It's that bracket. We're going to use squiggly bracket. That had to be necessary. Again, I don't know how to do that, so we're not going to. So the first step is write this expression, which is lazy sort of, as the really clever unit step function linear combination expression. And now we're just set up, because it's a linear operator, we can apply the Laplace transform to f of t. And that is going to be the Laplace transform of e to the t plus 1 minus e to the t u of t minus 2. And now what I'm saying is the linearity of the Laplace transform says I can split this sum and I can spit out any scalars that I want. So this, first of all, let's actually write that out a little bit. We should have distributed that u of t onto the two terms. But this is the Laplace transform of e to the t plus, I will distribute it in here. So this is going on to here and here, and then I'm splitting the sum. This is the Laplace transform of just u of t minus 2. And then in the last one, I'm going to get minus the Laplace transform of e to the t times u of t minus 2. When you've done this correctly, sometimes, and it rarely happens, they give you a function g times a unit step function. That's what we're trying to get. In the rare instance where I don't even know why they give the formula in the back of the book for this Laplace transform, quite honestly, but sometimes you will get the shift of the function g to have the same shift as the function u. In most cases, this is really hard to cook up, and there's no point even trying to do it. They give us the Laplace transform formula for doing an arbitrary function times this times any unit step function. So that's what I'm going to try and do. Just keep the shift in the unit step function, keep the shift out of the second function g. When we do this, I've now applied the Laplace transform to f, which I wrote as a linear combination of functions or unit step functions in combination. Then I split it using the linearity of the Laplace transform. And now what I want to see is if I've done this correctly, and now I want to use the Laplace transform table so that I've memorized them all, Now what I need to know is the Laplace transform of e to the at, and I will need to know how to do the Laplace transform of u. Some of the terms will just be, if you have just constants, some of the terms will just be unit step functions that I have to take the Laplace transform of, which we have a formula, which is e to the negative as over s. Anyway, we have a formula for that guy, which I already have in my mind, or you memorize in your formula sheet before you go in. And then we have a formula for doing a Laplace transform of a g of t times a unit step function shifted. And that'll be our next step. Step 2, use the linearity of the Laplace transform to split all of the sums and spit out all those scalars so that you have the Laplace transform of lexicon functions that you should know what the Laplace transform is. Laplace transforms of unit step functions, which you should know what the Laplace transform is by now, and the Laplace transform of, this one's going to be a little bit more complicated, but the Laplace transform of a function of t times a unit step function shifted. Let's do that. Move it up. Now that we have it at the top, what we're going to do is I've used the linearity of the Laplace transform to split all of these, and then I'm going to use the formulas. Let's do the easy. You don't have to crack each egg all in the same line. I know how to do this one now because I have a formula. I know how to do this one to do a formula. This one's a little bit more complicated, so I'm going to crush out those two right away, and then I'll refocus on that guy and get him in the end, and then we'll clean everything up to get the Laplace transform. This one is the Laplace transform of e to the at is equal to what? 1 over s minus a. Our a is a 1 because we have just e to the t. So this first Laplace transform is 1 over s minus 1. Remember, these are all improper integrals, which are horrible to calculate. You do want to, I'll rarely say it, but you should probably be memorizing quite a few of these Laplace transform formulas. This is why it makes it so slick and so easy from the student's point of view, because you forget every time that this, to find this was to compute that horrible improper integral. Formula. Plus the Laplace transform of u of t minus a is equal to e to the negative as over s. Again, improper integral that computed. Magic. He's just 0 or 1, remember. What does that give me? My a is 2, so that will give me e to the negative 2s over s. This one's a little bit more complicated, but what I'm going to use now is the Laplace transform formula somewhere in the back or the front of the book or somewhere that gives you, hopefully they are, this is where you should use this one. If I have a function of t times a step function shifted, that's what I was saying, they also have a formula where g is shifted and u is shifted, but it's so hard to get them both to be like that, just ignore that. Once I have this, this says that this is the Laplace transform of gt plus a, so if I put a plus into the g, and then times e to the negative as. So I'm going to do that move to this function. My g is e to the t, and my shift is 2. And I'm using this formula. So plus, and I'm going to do it in steps. First it says, and then I'll figure out what the Laplace transform of this shift is. First it says, because I have the 2, it's going to be e to the negative 2s times the Laplace transform of this guy shifted plus 2. So that will be the Laplace transform of e to the t plus 2. I'm going to use linearity of the Laplace transform and an exponent law again quickly. Exponent laws, they're everywhere. This is, I'm going to write this out again, 1 minus s plus 1 over the exponent becoming positive gives me s e to the 2s plus, this is also 1 over e to the 2s times, now what I'm doing is the Laplace, I'll do it slowly I guess. This is e to the 2 times e to the t. I didn't want to do that step because I know where I'm going with this, but if you haven't seen, I guess I should show you. First I use the exponent law to get rid of that. It's just a number now, e squared. What's e squared? I don't know. 2.7 to the power 2 to multiply by itself, a number. Well, that's another video we're going to do. It's definitely transcendental. 2 is algebraic, so e to the 2 is transcendental. This is just a number though, so I can pull it out because Laplace transform is linear. So this is equal to 1 over s minus 1 plus 1 over s e to the 2s plus 1 over e to the 2s times e to the 2 times the Laplace transform of, look, now that I've cleverly used the rules and I know what I'm doing. Oh, so I just did that one again. So not now, I will be lazy. The Laplace transform of E again now is 1 over s minus 1. That is essentially the Laplace transform of our function. Let me clean that up one more time. The Laplace transform of f of t, which was the Laplace transform of e to the t times 1, which was more importantly the Laplace transform of e to the t we found, plus the Laplace transform of the shift unit step function shifted by 2 to the right 2, plus the Laplace transform of e to the t times that step function shifted by 2 is now equal to, this is 1 over s minus 1 plus 1 over s times e to the 2s. This was a minus, I'm pretty sure that was a minus, there was a minus in there. Minus the Laplace transform of this is now, I'm going to combine these two guys now. This is e to the 2 minus 2s, I brought him up, times 1 over s minus 1. I really can't help myself. This is the same common denominator, so I'm going to add those. We could add all three, but you could just choose. In the book, and what they cleverly try to do is hide it for you. So this is how they'll hide that. They'll write that as, we can add these, so that's 1 minus e to the 2 minus 2s over s minus 1 plus 1 over s e to the 2s. And then what they really try to like to do to you in the book and stuff like that, again, certain calculus textbooks, I won't mention any names, but he's a real jerk, and in the back when he's supposed to be helping you to give you the answers, he likes to algebraically change everything, so they just like, ha ha ha, it is what you got, but I use rules. So he's gonna, I've seen what they do, and with this one, they know the formula is e to the t is 1 over s minus 1, and they know also you hate negatives, so they take a negative out of it. So he does this. 1 over, or sorry, I'm gonna write this as e to the 2 minus 2s minus 1 over 1 minus s plus 1 over s e to the 2s. And then he writes the final answer like this, and you're like, that's not what I got. Yeah, it is. He just cruelly took a negative one out. Why do they do that? I don't know. But I'll start pointing those things out to you so that you, caught you. That's what they're doing. There's the Laplace transform of this. Please subscribe below. Ring the notification bell. We're going to do more of these. This isn't even the complicated one. The bee's knees is using Laplace transforms to apply it to and solve systems of ordinary differential equations. See you next time. Yes, where are you, cameraman? Just kidding. I throw him under the bus anytime I can.